exactly whether you have one or many particles. Right? And the way that we can diagnose that is looking at the variation in the energy, the variance in the energy operator, the Hamiltonian. And if the variance in the Hamiltonian is larger than the typical energy required to create a particle, then it's impossible to decide whether you have one or many particles. So in particular, you can see that if you try and localize particles exactly, to actually perform an experiment where you would diagnose whether particles travel faster than the speed of light, you can never tell whether you're actually studying one or many particles. And the very notion of what it means to have a single particle as opposed to many particles is one that you have to consider very, very precisely. And that's exactly what we're going to do. So this leads us naturally to the question, is how do we construct a theory of multiparticles allowing for variable numbers of particles, so processes that change the number of particles, and in particular allowing for the creation and destruction of particles. I should actually mention as an aside that although I'm introducing the subject of particle creation and destruction in the context of relativistic quantum mechanics, it's also a theory that has many other applications. So for example, in materials physics and condensed matter physics, this is something that we consider all the time. So the low energy excitations of some material can be described effectively as particles. And we actually saw that when we developed the Debye model. When you guys developed the Debye model of solids in one of your problems, you saw that there were phonons, which are these particle-like excitations of materials. And indeed, it's frequently the case that the low temperature behavior of all sorts of materials are described precisely in terms of the sorts of multi-particle Hilbert spaces that we're now going to construct. So our goal then is to construct a Hilbert space which includes not just the single particle states labeled by momentum k, but all sorts of other states as well, where you can have an arbitrary number of particles. So the way that I'm going to do this is I'm just going to first define for you the Hilbert space and write down for you the natural Hamiltonian, and then we'll try and understand what the natural operators and observables are for that Hilbert space, which will give us a nice physical interpretation for our theory of particles. So if you're going to have a Hilbert space which has particles that can, with a number of particles that can vary, then the first thing you want is you want a state in your Hilbert space where there are no particles. And then we also want a part of our Hilbert space where you have one particle. So these would be the usual one particle states that we were considering earlier that would be labeled by their momentum k. But we would also like to have two particle states, which will be labeled by a pair of momenta k1 and k2 of our two particles. And I would like to describe a theory where our particles are indistinguishable, so that the state is the same if you switch k1 and k2. And so on and so forth. We would have 3 particle states specified by 3 momenta, 4 particle states by 4 momenta, and so on and so forth. And the simplest way that we can imagine constructing such a Hilbert space would be just to take the Hilbert space spanned by this no particle state, so that's a one-dimensional Hilbert space, called H0, and the Hilbert space spanned by our one particle states, okay? That's the usual Hilbert space that we always consider in quantum mechanics of a particle in 3 dimensions. And then we would like to add to that the Hilbert space H2 with 2 particle states, and so on and so forth. And our total Hilbert space will just be the direct sum of these guys. What does that mean? It's the Hilbert space spanned by the set of all basis vectors, where you specify first the number of particles, and then you specify the momenta of each one of those particles. And this is often known as a box space. That's just the terminology. So, for example, the identity operator in this Hilbert space is the identity operator in H0 plus the identity operator in H1 plus the identity operator in H2 plus so on and so forth. The only subtlety being that we need to include a factor of 1 over 2 here to account for the fact that when you integrate dk1, dk2, you're actually over-counting because you have that symmetry that interchanges k1 and k2, so I've included a factor of 2 there to account for that. And that is actually not just a factor of 2, but it's a factor of 2 factorial, also known as 2. But I write that factorial symbol there because it makes it clear that when you write down the dot 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 terms, you'll have a 1 over 3 factorial, 1 over 4 factorial, and so on and so forth. Okay. So in order to parameterize this Hilbert space a little bit more efficiently, I'd like to come up with a new way of labeling our basis states. In particular, I'd like to label each basis state by a function that I'll call n of k, where n of k is the number of particles with momentum k. And I'll normalize it to have a delta function, so that, for example, the state k1, the state where you have a single particle with momentum k1, is described by the function n of k, which is a delta function, k minus k1. I suppose I should write that as a 3-dimensional delta function. the state with two particles with momentum k1 and k2 is given by the function n of k, which is the sum of two delta functions. 1 at k is equal to k1, and 1 at k is equal to k2, and so on and so forth. So a basis state is then, so a generic basis state is then labeled by a function n of k. And we can then define the operator. Capital N, which measures the number of particles with momentum k, so that n of k, acting on one of these basis states, which is given by that sum of delta functions. Why is that useful? Well, it's useful because it gives us an extremely compact way of writing out the Hamiltonian. The Hamiltonian